The environmental conditions on alien worlds are, to put it lightly, extreme. Enceladus has geysers coming out of its south pole. Venus is draped in clouds of acid, and Io oozes with molten lava. To find out how scientists are studying these dramatic celestial bodies, today we are joined by Professor Brian Cox to discuss his new series, Solar System. Thank you so much for joining us today. And can you tell us a little bit about the series?
Yeah, in some ways it's a sequel of sorts to Wonders of the Solar System, which is the first big series I did with the BBC. And so why a sequel now? Well, a lot's changed. We hadn't been to Pluto, for example, back in 2009. And our knowledge, I think, of the moons, particularly the Juno spacecraft around Jupiter, for example, has delivered quite a great deal of new insight. But also, it's very different. The first series we did, as with most solar system series, is pretty much focused on the planets themselves. Whereas this is focused a lot on smaller objects, Ceres, for example, or Triton, Neptune's moon, and why, even though it's of a similar size and composition to Pluto, it's significantly different. So it's about the solar system as a system, rather than just the individual planets. And also in style, I think it's very different to anything we've done before, because we went back to basics in many ways. So one of the things that was central to the series was doing sort of experiments that in many ways would be, school experiments that students do at school. So little simple experiments to demonstrate physical principles. But the physical principles that are very relevant indeed to quite deep questions about the way the solar system operates. So one example in the first episode is a very famous experiment where you take a hard-boiled egg and a raw egg and you spin them, and they spin differently. The thing with the fluid inside wobbles around because the centre of mass moves around and the interior is not linked to the exterior and so on. But those techniques are the modelling techniques that we're using to try to understand whether Enceladus around Saturn has a subsurface ocean. So it's basically the same physical principle. It's the wobble of this moon as it spins on its axis and orbits around Saturn that's leading us to suspect that this may be not just small pockets of water on that moon, but perhaps a subsurface ocean on the moon. So it's that was very different to sit there and do little experiments, school experiments essentially, to demonstrate, as we all know, that this very central idea that the laws of nature that we see here on Earth are also applicable out there in the wider universe.
That is really, really, really interesting, connecting the science that maybe a member of the public have done in school or their children are doing right now to the bigger mysteries or bigger objects, smaller also objects in the solar system. Among the many places that you visit in the series, is there some that have a special place in your heart?
Yeah, I mean, one of them, there's an episode on ice, essentially, which is, again, I should say each series, the first program is really a program about thermodynamics. The third program is really a program about chemistry. And the fourth program is about ices, I should say. And one of the most remarkable things to me, we filmed in Alaska, which is always beautiful. I've only been there once or twice, and it's just magnificent. On Denali, which is the glacier and the mountain itself are just like nowhere else on Earth, essentially. And so it was a spectacular location. But the thing that I hadn't really understood is when you fly over a glacier and you see these structures on the glacier, and it's like a flowing river, but in ultra slow motion, the way these things flow. So there are rapids and still areas in the glacier. So you see these structures which are essentially frozen sort of turbulent flow. That's probably not correct from a geological perspective. Any geological, they will say it's not turbulent flow, but it's the equivalent of rapids in the river and the equivalent of smoother flows. And you see it. And we flew, it was the helicopter pilot who we were working with told me about this, and he was pointing all this out. And then, of course, you look at the images of Pluto from New Horizons, and you see that behavior. You see the same behavior, But it's extremely cold on Pluto, of course. What was it, minus 220 degrees or something? It's Celsius on the surface. It's very cold. But the key point is that the nitrogen glaciers on Pluto flow in a very similar way to the way that water ice glaciers flow on Earth. And the reason is that the nitrogen in that regime of temperature and pressure is relatively close to its melting point underneath the glacier, which is the same. That's a lot of the dynamics on Earth are driven by that closeness to the freezing point of the water on Earth and the nitrogen on Pluto. So they behave in the same way. So it was so wonderful to see a landscape on Earth that is such a good analogue for a landscape on Pluto, even though the building blocks are different, but the physical behaviour is very similar. And I think that was really beautiful.
I absolutely love that you can make this connection between our planet and the other bodies in the solar system. You already mentioned Alaska, and I'd really like to ask a little bit more about location here on Earth. Is there a particular location that you found absolutely fantastic, maybe not what you were expecting?
Yeah, I mean, Alaska is one. Another one we filmed at was we started essentially in Salt Lake City and went down through the spectacular landscapes and canyons of the American West. There's a place called Moab, which has become kind of a town that's it's kind of quite, it's a tourist attraction now, but it was the wildest town in the Wild West, this place. For years it was one of those typical, you should have cowboys going through this town, right? It looks
frontier
like
town.
It absolutely is that. But then it became the centre. They discovered uranium there in the 50s. So it became this very rich town where there's a uranium rush. And so there's all these places in there which are called the atomic hair salon and the nuclear coffee shop and the uranium building. And it's all that 50s Americana kind of thing. But also we're filming there because it's a film about atmospheres, planetary atmospheres. Mm-hmm. And you get structures that develop in the atmosphere there, dust devils, for example. And dust devils form in instability. It's all about thermodynamics and chemistry again. It's about gradients equalizing and spin and other things. So, but these structures that you see out in the desert there, we saw, to everyone's surprise, I think, on Mars. And there's a beautiful story where, so the rovers, the little rovers, the Spirit and Opportunity, when they landed on Mars, they were thought they're solar powered, and it was thought that they'd become covered in dust and they wouldn't last very long. They lasted, of course, for years and years and years. And the question was why? And a large part of it was dust devils cleaning the solar panels on Mars. So the dust devils were forming and taking the dust off the panels. And so these rovers lasted 10 times, whatever it is, longer, way longer than their design life. And so, but again, it's where you can see these seasonal instabilities in the atmosphere of Earth. It's very clear in the American West. You get these monsoon sort of structures and you get these flash floods and things, and you get them on Mars as well. So the analogue is very beautiful. And of course that landscape looks like Mars, although it's very different. And so again, I thought it functioned really well as a place to tell the stories of the atmosphere of Mars.
That is absolutely fascinating. When you mentioned dust devil on Mars, yes, they were so important for Spirit and Opportunity, but my mind just goes to insight and perseverance and curiosity that have been able to document so many more dust devils.
Yeah.
And that it was something I think none of them, maybe not, even Curiosity got to Mars in 2012. So you had not that kind of information for the previous series.
Yeah.
How did all
we have photographs, we have movies of dust devils on Mars.
It's incredible.
Which is great.
Is there a particular piece of new science that just came out recently that you really felt we need to have this in because it's so important?
Yeah, we had some really current pictures from from this year of Io and the volcanoes on Io. And in the one of the episodes we talk about Europa, so we're quite focused on Europa. It's the ice episode, And there we had one of the physicists who was on Europa Clipper out with us from JPL in Alaska. And so we got into some detailed conversation about why it is that in some people, in the planetary science community, there's quite some competition between, certainly in looking for life. So some people think Mars is the thing, some people think Enceladus is the thing, some people think Europa is the thing. But the Europa community point out that part of the reason that Europa is thought to be a potential habitat for life is the chemistry, the surface chemistry, because life is it's not only about thermodynamic gradients, it's about redox potentials and things. It's about can you have the chemical reactions that allow electrons to move from electron donors to acceptors, all that stuff that you do at GCSE and whatever, right? So that chemistry is suspected to be present on Europa because of the material that's deposited on the surface of Europa from the volcanoes of Io. So it's a very and the big question, one of the big questions that Clipper and Juice will answer, is whether that material can get into the ocean. So is the geology of the surface, of the ice surface, such that you have access from the surface down into the ocean? Because if you do, then you have the electron donors and receptors that you might need in the ocean, but it depends on those cracks to some extent. So we got into some detail about that, but it's a fascinating picture of this system that's developing from Juno observations and also from sort of some more advanced modelling of the system. That if you think about it, you've got, why is Io active? Because of an orbital resonance with Europa and Ganymede, right? So you've got these three moons that are acting in concert to keep Io active, which we do in the first program of the series. And also Europa, by the way. So Europa in its elliptical orbit, so tidal heating giving you the ocean. But then, if it's also the case that the chemistry, the geochemistry and potential biochemistry of Europa is fed from the volcanoes of Io, you've got this picture of this complete, all the energy is coming from Jupiter, and you've also got the radiation belts which are modifying the chemistry on the surface of Europa as well, which might be relevant. So you've got this extremely complex system. So this habitat, and this is central to the series, I think, this potential habitat on Europa is not just Europa. It's also certainly Jupiter, but also potentially Io as well. And I suppose Ganymede in that case, because of the system. So you've got this interconnected potential for a habitat, which I love. And that's pretty new thinking. And I wasn't really aware, but we put it into the show because it came from conversations that we had on location. But one of the goals of Europa Clipper and Juice is to see whether that story stacks up. Because we don't have that much information, actually. We have quite a lot about, but we don't really, is that right? That whole idea? We're not totally sure.
I love the story. Obviously, if we were to find life, that would be revolutionary, but already finding that disconnection, what a story.
And it's central, again, the whole series has this idea of treating the solar system as a system. Some of the early discussions we had with some of the planetary scientists to see what's the underlying philosophy of the series. There's this idea there's an idea called comparative planetology, or comparative, I suppose not even planets, but comparative. The Triton and Pluto is a beautiful example, actually. Two objects that are basically the same, but they're not because their histories and their position in the solar system is different. So you start to learn about this thing as a system and see it as a system. And that was very different to the way that we thought in 2009 in the series. And perhaps it's a rather more modern way of looking at the solar system.
We just stand on the shoulder of giants, and the approach to science has always been like we put nice little boxes, and I think now we're starting to consider like, why do we actually use the boxes when we start seeing the connection and the differences of things where should actually just be the same.
Yeah.
To conclude, I'd like to ask, what is your personal hope that the audience will get from this series?
Beyond just the fact that this exploration of our home system is important and valuable, there are some key ideas in the series. One is the experiments that I do in the series are very important because they're showing how we acquire knowledge about nature and how we discern what's reliable and what isn't. And so that's in there. But also there's a sense, one of the planets that we've always struggled with in these series is Venus. Because Venus is a hard place to tell stories about, because you don't have beautiful images of the place, because it's very difficult to get a space probe onto the surface, and we haven't done it very often. But in this series, it became really central because of the study of plate tectonics. And so the question of why Venus does not have plate tectonics and therefore has volcanoes all over the surface, whereas the Earth, which is in many ways its twin, has plate tectonics and only has volcanoes therefore at the plate boundaries, which regulates the climate, which gives us a habitable world here, central to the habitability of Earth, plate tectonics, and central to the non-habitability of Venus, certainly on the surface. So why that's the case is not really fully understood. So it shows you that in trying to answer very important questions about Earth and its climate and how it works and how our planet came to be the way that it is, this laboratory of the solar system can provide you with answers because it provides you with different experiments. So nature's done a different experiment with Venus, and it's quite subtle and not fully understood. So the case for exploring Venus, which has been neglected, let's be frank, in space exploration, is very strong, I would say. And it comes through, I think, in the series. And it was partly my conversations with scientists working on Venus that led me to a new understanding personally of why Venus is so important. Because you tend to neglect it, don't we? I don't know why. We send loads, it's probably just easier. We send loads of stuff to Mars. And this planet, which is so intriguing, we really don't send much to. And so I came away with this newfound love for the exploration of Venus.
Well,
so I hope the audience see that as well.
I completely agree on we need more of exploration of Venus, and I guess so I will look forward to a third series on the solar system when we have the data from Da Vinci and Vision, and we will know more about the planet.
The pace of exploration is accelerating, I think, and some of it, I suppose, is due to the ease of access now. It's getting cheaper to launch probes. Mm-hmm. And easier to launch probes, but still, there's big missions. Uranus and Neptune. We've only been once. I mean, surely, and just went straight past Voyager 2.
Weird, and we need to understand it.
So we don't really have. We've got JWST images now, which are quite nice, but really, the case for a big mission, an orbiter, but both Uranus and Neptune, actually, I think is so overwhelming. If I was one of these billionaires that's floating around with all my money, I would fund 2 missions. I'd fund an orbiter to Uranus and an orbiter to Neptune. What a good use of money would that be?
I would completely agree, but I will throw a third mission because I really think we need to go back to Enceladus and understand it once and for all if there is good chemistry. We know there's chemistry there, but if there is chemistry that could potentially be biochemistry.
True. We need a probe that flies through those fountains, those plumes. I mean, because it's so obvious, isn't it? Because it directs access to the potential habitats without having to land. So I think we'll do that, though. So that's the thing. So I think the reason I would, in a philanthropic sense, if any billionaires that are watching and you think, what can I do? I would genuinely fund a mission to one or preferably both of those ice giants. Because I don't think we're going to do it anytime soon. Well, and it would be absolutely magnificent.
Yeah, especially to learn more about even Triton as this extremely weird moon.
We did in the ice film. We talk about the aurora on Uranus, which is potentially, in part, due to this strange form of ice, a conductive form of ice that sits below in the deep within the sort of upper interior, and because the conditions are so weird. And so again, you know, is that right? We don't know really. We don't have much data about these places, because Voyager 2 went straight through the system a long time ago. It was 86 when it went past Neptune, wasn't it? And so, you know, come on, somebody write a check.
Yeah, fund this mission. Well, with this passionate plea for more science mission at the edge of the solar system, thank you very much for taking the time to talk to us about your new series.
It's a pleasure.